Tomorrow we have an exam on everybody's favorite topic, condensed matter. I'm sure we've all heard about this stuff, but essentially it's when matter is kind of very compact. I mean, technically we're studying different kinds of matter like Drude metals. This is an important one. Sommerfeld metals. Let's focus on metals right now because essentially that's what we are doing. And this is for classical metals, the Drude model. And then we have the quantum model, which is the Sommerfeld. So the Drude metals follow Maxwell-Boltzmann statistics. We're talking about this particular equation here. E to the power of mu minus energy over kBt. And it kind of looks like this if we were to, it's really the, I think it's as temperature goes up, you could see that basically the line kind of gets more elongated. And as temperature goes down, then this line kind of becomes more close to these axes, squished in. So that's pretty cool. And you can see how the quantum model is for the Fermi Dirac distribution. So we have this particular equation that we focus on, and that's 1 divided by e to the energy minus mu divided by kBt. This mu is the chemical potential. And this is a +1 down here in the denominator for the Fermi Dirac. So this is kind of what fermions, like electrons, would do. Just kind of electrons near the Fermi surface is really what this equation is trying to do. You can see what happens here is that the electrons essentially reach a point where there's like the Fermi surface is filled up, and then the Fermi surface is empty, so there's no energy. And so then there's kind of the step function, yeah? But as the temperature starts to go up, what happens is the electrons are kind of excited, and so they kind of spill out of the Fermi surface, and that boundary kind of becomes a little bit more smeared. So you can see as temperature grows, these two charts begin to look a little bit more similar. So essentially the idea is that really high temperatures, they're basically the same thing. Okay, because basically if we have really high temperature, what happens is this denominator goes to infinity, and so this thing becomes e to the power of 0, which is 1. And over here, the same type of thing would happen on the bottom. This becomes, I think it becomes a 1. Well, that's weird. It's 1/2, and this becomes a 1. But yeah, I don't really know 100% about this stuff. This is kind of just, it's really complicated. Right? This is condensed matter, so I don't really know too much about all this. There's one third type of distribution, which is the Bose-Einstein, which is basically bosons. So we have to have something for like classical particles, which is the Maxwell-Boltzmann, and then we have the fermions, which is the Fermi-Dirac distribution, and then we have the Bose-Einstein, which is for bosons. And as you can see, the chart kind of looks like this. As temperature raises, it becomes very similar to the very first. It becomes similar to the very first thing. So they all reach sort of the same type of distribution if the temperature is really high. All right, and you can see how this one has the minus sign for the bosons. So that's cool. Now let's focus again on the Drude metals, which is more classical, the Maxwell-Boltzmann distribution stuff. Let's go back to this. Let's look at the DC conductivity, which is kind of the most important part of the Drude model, is that the conductivity in the metal is defined as N, which is the density of electrons, times E squared, the electric charge, times this tau, which is the scattering time, divided by the mass. So this is the conductivity, and that's DC conductivity in the sense that I guess it's constant. If you have AC conductivity, then you have this sort of sinusoidal situation, and so then you have 1 minus IWT at the bottom here. And of course, we don't really like that complex stuff, so we usually take the real part of it, resistance here. That's just going to be sigma divided by 1 plus w squared tau squared. All right. So this is kind of the AC and DC conductivities that we get from metals. And let's also take a quick peek at, say, this thermal conductivity business. I think it's better to do it here. This is the Wiedemann-Franz law, so Drude kind of does it incorrectly. Drude has this K over sigma times the temperature. This is temperature here. And we're trying to figure out like thermal conductivity K. So he kind of says that it's like 3 over 2 divided by KB squared over E squared. And that's not correct because, well, it's kind of a classical result. But the metals are really more quantum-like. Like this is a more accurate model over here. You can see it's like pi squared over 3 times KB squared over E squared. So this is a more accurate model. And we can use the specific heat now. CV equals pi squared over 2 NKB times temperature divided by temperature final. Not 100% sure where this is supposed to sort of relate to all of this, but it seems related. Keeping in mind again that this is a really complicated topic, so I don't really know. I think that this 3D specific heat metal, we have to add the two types of specific heats. One is from the Sommerfeld model, this gamma times temperature, and that just kind of comes from this, as you can see here. This is the Sommerfeld part. And then the Debye specific heat is this. It's a little bit more complicated to calculate it. So, yeah. But we have this huge thing that does specific heat. Alright, so we kind of have thermal conductivity K, specific heat CV. We focused on the distributions, and we focused on these conductivities over here. Resistivity is just going to be the opposite, the inverse of conductivity. You can even turn it into a tensor-like object here, which is kind of cool. We have mobility, which is going to be Q, the charge, times the relaxation time, divided by mass. Some skin depth. I think this is when there's like a wave that's going to essentially penetrate into that that lattice. You see kind of a skin depth right there. So that's the surface of a metal. Alright, yeah, so here's another way you can sort of build this conductivity field or the conductivity tensor up, which is nice to know. But let's head over to the Hall coefficient. You're probably more familiar with this version, 1 over n times charge. Although there's other ways to write this. I guess that's the Hall coefficient kind of tells you, like, it tells you what the density and charge of carriers in the metal. So it's a useful number to know, the density and the charge of the carriers. Yeah, the lattice oscillations will be interesting in just a second. Let's see what else we need to know here. The density of states. What is the density of states even trying to say? Let's focus on like this type of thing? Well, we have like massless particles and massive particles, like photons or electrons. The density of states, gosh, I don't even really know what the density of states is trying to say. But it could be, we're trying to figure out how many states there are for that particle. I'm going to do a little research on this density of states business. Density of states. Yeah, how many quantum states are available per energy interval? Density of states. Let's say available states. At energy. Let's just call it E naught. So you choose some energy and you figure out the number of available states. And that's essentially what the density of states is. So let's look at these massless terms. The idea is you're following this format where you have VD, and VD is just the length, the area, or the volume. Then you have the omega D, which is either 2 pi, or 4 pi, based on whether you're in 1, 2, or 3 dimensions. And of course, D is 1, 2, or 3 in this case. Let's try D equals 1. That's a pretty easy one. You just plug in L divided by 2 pi to the first power. There's a 2. And then we have K to the 0 power here. 1 divided by HC is because if you rearrange this energy term into the K, and then you take the dk over E, and that'll give you 1 over H bar C. So that gives us the one-dimensional density of states for this particular area. Oh, hey, how's it going, you guys? Hey, I barely understand this stuff too. Yeah, this is tough. So this is kind of what I'm trying to study here. And we're just looking at the density of states in these various dimensions. So, you know, you just kind of plug them in. So you got the area or the volume, it's 2 pi squared or 2 pi to the third. You have the 2 pi, or the 4 pi, depending on whether it's 1, 2, or 3 dimensions. And you're just taking this derivative in terms of dk, dE. It's always the same. So just plug that in here, plug that in here, plug that in here, and plug that in here. Or, you know, then you have to count up how many k's you have. So k, d minus 1. And you just basically put k 0, k to the first power, which is that, or k to the second power, which is this. And ultimately, you can sort of do that with the massless version, the massive version, and it's a little bit more complicated of a calculation over on this side. So this is how the density of states works. Now let's talk about this Fermi stuff. So Fermi is interesting. He basically created this Fermi sphere, the Fermi surface, where you're filling up all the states with electrons. And the left side here is essentially electrons moving to the left. And on the right side, we have electrons moving to the right. So they kind of balance out, and this is sort of an average velocity of 0. Now, if you apply an electric field, you can actually shift this Fermi surface more to the right or left, and so then you could basically start moving the electrons. Now, it's important to know that okay, this is a little bit crazy because we have two spaces. It's very important to know. There's a real space where the electrons are like literally moving. So the electrons move in real space. But then we also have this momentum space where we have filled states. Yeah, why are the electrons bouncing? So they're always moving around. Electrons are always zigzagging around in it's really, really fast, right? So you kind of have to count up how many electrons you have and figure out like how many are moving to the left, and then how many are moving to the right, how many are moving up, how many are moving down, and you've basically filled this little momentum space with sort of a quantified number of how you're counting how many electrons are moving up, down, left, or right in momentum space. And you're sort of making this little ball, and you're calling it the Fermi surface. Now this ball can be shifted to the right or to the left if you apply a force, which basically says, okay, now there's going to be less, if we move it here, now you can see how there's less electrons moving to the left and more electrons moving to the right. But we didn't yet move the electrons. Like, we're looking at momentum space right now. We're just looking at the number of states being shifted. But the electrons are actually moving in real space, like elsewhere. So it's kind of a different description of real space. We're kind of like looking above and counting how many things are moving in different directions, and we can shift the count up, we could shift the count down based off of all this stuff. And so we have a question that says, analytically continuing the vibronic quasi-particle manifold, definitely makes sense there, into imaginary K-space. Does the fermionic topology become an adiabatic non-abelian Brillouin? I'm not exactly sure whether there's adiabatic or non-abelian stuff going on, but I do know that about the Brillouin zone a little bit. I know that the Brillouin zone is essentially just a cell block, like a Wigner-Seitz type of cell block that we're building out of the reciprocal space. And the reciprocal space is the momentum space. And the thing is that I'm not entirely versed in this stuff yet, so I don't actually know anything more than that in terms of like, I know what the Brillouin zone is, but I don't know about how the analytic continuation of the quasi-particle will work in terms of this. So talking about real space versus momentum space, when I say real space, I just mean where the electrons are actually moving in space. Like, you know, if you look at an electric current, the electrons are actually moving very slowly down the stream of like the current. So that's in real space. But you can also count in a completely different space, like a tangential space. You can count how many are moving to the left or the right or up and down, and that has to be done not in real space. So that's kind of the main difference, whether you're counting stuff or whether you're watching stuff actually move. So that's kind of the main difference. And that's why it's kind of a quantum theory, because we're just counting stuff. We're filling states. So these are really good questions, guys, and I'm glad you're testing my knowledge on this stuff. But unfortunately, I'm not a pro yet, so it sucks. All right, so let's look at this Fermi stuff. So the mean free path is interesting because it basically tells you how far something's going to travel before it scatters again. So here's a scatter event, and here's another scatter event. And that is the L that we track right here, which is we need some velocity and some decay time, I suppose, that will give you this distance. It's the time between the scattering. We have some more questions. So it says, how do we know, if it's not real space, why don't we study the real stuff? Yeah, you kind of have to study both spaces. So that's why if we go down here, to the vectors, like if we look at a crystal lattice, we'll notice that the real space vectors are this R and then you just use A1, A2, A3 to give you your X, Y, and Z axis, so you can build like a crystal lattice. And if you go into momentum space, which is not real space, but momentum space, which is kind of counting like the motion of particles, then you have to use these reciprocal vectors. But notice how they're tangent to each other. So G times, or G dotted with R, e to the I G dot R is going to be equal to 1, basically telling us that these spaces are tangent to each other, and you can see how you kind of flip them. So one of them looks like this, and the other one kind of looks like this, and you can see how that might look in terms of rotations here. So they're very much related to each other. It's just that we have to study the state space, which is the reciprocal space, in order to really understand what's going on in real space. So that's kind of what the difference is here. There's some interesting questions. Thanks, guys. Thanks for the good questions. Yeah, it's a good question. Why I'm doing gang signs, man. You know, I used to do rap, so it might just be you know, ingrained in my muscle memory. Okay, so let's look at some of these Fermi numbers here. The Fermi velocity is important because it'll give us the momentum. If you take the mass times the Fermi velocity, you get momentum. Fermi momentum and the k, the wave vector, they're related by this h bar. So P equals h bar k, and k is what we really need to know here. It's the 3 pi squared n to the power of 1 over 3. The momentum is basically h bar times the 3 pi squared n over 1 over 3. And these are all really important values because, you know, if you want to find the Fermi energy, you have to basically do this, where you take the momentum squared divided by 2 pi, and that'll give us the Fermi energy, which is really kinetic energy, that's at the Fermi level. So right at that blue boundary, there's a specific kinetic energy of the electrons, and that would be this. H bar squared over 2m, 3 pi squared n to the power of 2/3. Now another question says, why do electrons only come in pairs of 5? And I'm wondering where we got that. I'm not exactly sure. I think electrons only come in pairs of 2 because of their spin states. An electron has either spin up or an electron has spin down. And so that kind of makes this Pauli exclusion principle that if you're filling up a zone with electrons, like this cloud right here, it can only have 2 electrons, and then at that point you've maximized the number of states that are available. So that so you have to fill up a new cloud. So every cloud can only contain a maximum of 2 electrons. This is the Pauli exclusion principle right here. But I'm not too sure about whether they can come in 5s. And yeah, so this topic here is condensed matter, so it's kind of like a physics-y type of thing, but it's very similar to chemistry. Chemistry and physics, they're kind of coming together here, because we need to understand matter. So let's look at the crystal states again, because this is kind of where we have to end, where we're ending our kind of, our exam is going to be on this crystal lattice stuff. So we had the direct lattice vectors, the real space vectors, and the reciprocal space vectors. Oh, you mean these things, these 5 right here? Oh, that's just like basically one unit cell. It's just kind of a representation. It's going to be like an infinite lattice really here. There's a lot of points in the lattice. So here's another lattice, for example, has lots and lots of points. And these are actually not going to be electrons. These are atoms. So these are actual atoms here. These are atoms. So for me, the exam is tomorrow. So I'm just trying to finish up a little bit of studying here and try to figure out what all this stuff means, because it's so complicated and there's so many topics. So in order to find the reciprocal vectors, we have to rely on our direct vectors, which is our in real space. We take the cross product, like you say, like if you want to find B1, you go A2 cross A3, and then you divide it by A1 dot A2 cross A3. And of course, that's going to be the same denominator across all three. And this is sort of a cyclical, if you want to find B2 and B3 and 3, then you kind of start with the next number. So B2, and you're going to go A3 cross A1. If you want to find B3, then you go, let's go A3 cross A2, or A1 cross A2. And boom, now you have your reciprocal lattice vectors. So here's a little example where we take our points and we sort of figure out, okay, if we go to the right, then we have A. If we go up, then we have B. So those are two lengths. And if we take the center right here, then that's A over 2, B over 2, right? So we can make this lattice with primitive vectors, the smallest possible vectors that will construct this lattice right here. And it requires A over 2, B over 2, and then A over 2, negative B over 2. So when you repeat this, you will build the lattice. And here's another example of how we take this particular lattice and we find two vectors, A and B, or sorry, A in the y direction, A in the x direction, like this, and that constructs the unit cell. And as you can see, we have 1, 2, 3, 4 of them. This stuff just repeats a bunch of times, and so that's kind of what we're doing. If we have weird displacements, we just have to realize that these primitive vectors have to repeat, like it has to work, it has to be the same. So over here, if we go from the open to open, we have A spaces. Same thing with the close to close, we have A spacing. Over here, it requires 2A to go from close to open to open, but we could still go A between the closed. But that's not going to do. It has to be preserving translational symmetry, and so therefore we have to use 2A for both X and Y. Like, you know, it's not going to work with just an A. It would only work if both of them were translated by A. So here you have to use 2A as sort of the minimum possible vector size. So that'll create the entire lattice if you repeat it a bunch of times. Now, it's important to know the difference between the basis and the lattice. The lattice is simply the points that we have, and the basis is going to be like the atoms that are like around the points. So, so that's interesting. Now he asks, how do we draw a Lewis dot drawing of CH4 because I have leftover atoms? That's a good question. Let's see if I can actually remember how Lewis drawings work, because I know that I think Lewis has something to do with these things. And if I can remember, I think C has 4 to begin with, and H has 1 each. So I would assume that we do something like this. We attach an H on each corner, and that should fill up the Lewis structure. Although I'm not 100% sure if this is correct, but I think it might be. So that's kind of cool. I'll just make sure that this is the Lewis structure right here. So that's kind of similar to what we're doing with these lattices, except we're looking at like repeated structures. So this is like one molecule, but in the crystal lattice, we might actually have like a C, a C, a C, 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 and then we might have some like oxygens in between. And so you kind of build a little crystal, like a CO2 type of crystal, which is kind of like that. So that's kind of the difference between a Lewis atom and, oh, hey, you're listening to one of my songs. That's crazy, man. Yeah. I used to write music, and that's just like one of my songs. I think I have like 100 songs or something, but I'm not very popular. So that's rough. Thanks for listening to my songs. Yeah, so these are the electrons that are shared, right? So you got 2 shared electrons. So the hydrogen has 1 electron. And I'll go ahead and color these, or color code which comes from which. So the carbon has the blue, and the hydrogen has these reds. So we're kind of sharing these across. Got to make sure that we always dot the correct one. So the one on the right is blue, the one on the left how are we doing this? I don't know. One of them is supposed to go for the other one. Boom, 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 boom. I think that works. And that's how they share the electrons between each other. Yeah, really interesting question. But the crystal is more of a lattice that repeats like this. So you have a bunch of atoms sort of jammed together. And that's what the Bravais lattice is trying to explain. So you can like pack stuff together really closely. So for example, we have a simple cube which might have 4 atoms on these corners. 1, 2, 3, and 4. And if we wanted to find the volume of the ball, it's just 4 thirds r to the third, right? But if you find the volume of the cell, it's a to the third, and one of these sides a's is equal to 2r, and so therefore we kind of get this this ratio here. And the Brillouin zone. A fretboard pattern, yes, I would say that a lot of these things in terms of physics is very patterny, like. I do think of scales, like a musical scale, in terms of like going around a circle like this, so you could have the different letters at each one of these points. I used to think about that in terms of how are we going to like go around the octave through a scale. You got like 7 or 8 notes or whatever. Okay, so we can go to the body center one, which is basically like this. You have to connect this corner with the far corner, and you get this huge long diagonal, which is a squared to 3. And if you count up the r's, 1, 2, 3, 4 r's is across this very long diagonal. So you kind of have this type of ratio. Noticing that the body is 1 atom, and each one of these corners is actually 1/8. And since we have 8 corners, that just equals 1 total atom. So we're counting the number of atoms in these boxes. We have 1 in here, because there are 8 corners and each one is 1/8. Here we have 8 corners, each one is 1/8, and then there's one in the center body. So there's two in total for this cube. In this one, we have a cross, like an X, and the only atom that we have here in the center is on the face. So the diagonal here is simply a square root of 2. And we can count up 1, 2, 3, 4 radiuses across this length, and so we get a different ratio. The 6 faces, each face is 1/2 of an atom. So that means 1 atom for the 8 corners, and then 6 faces times 1/2 gives us 3 more atoms. So we have a total of n equals 4. And on this final one here, we have the diamonds, where we sort of split the, we have to double the atoms that are in the face center. So we put one at 0, 0, 0, we put one at 1/4, 1/4, 1/4, we figure out the length between them, which is 2r, and then we just multiply it by this ratio here, and we get the square root of 3a over 4. And this is how we do diamonds. So we kind of have different ways to calculate how many atoms are in a cube, one of these Bravais lattices. Yeah, I definitely enjoy looking at string theory and fundamental frequencies and all sorts of cool stuff like that. That's kind of what physics is all about. Like, I used to play music and stuff and think about octaves and frequencies all the time. And then going into physics, it was just natural. Like, we have to confine these wave functions into specific constraints with boundary conditions, and then of course the different frequencies that, like the harmonics that you can go to. So that's definitely cool. I think we've pretty much talked about everything we need to know for the crystals and the Bravais lattices. Here's the diffraction, where you kind of have to look at the scatter angle. But I think we know this formula, n lambda equals 2d sine of theta. We've done this many times before with X-ray diffraction. Alright. So that was basically everything that we needed to know for this exam, to be honest. That's quite a good review. The Brillouin zone and the Wigner states, yeah, this is kind of the last thing. We do need to, basically, if we have a lattice, and here are the lattice points, all these black dots. Black dot there, black dot here, all these black dots here, and we have a center, then we have to basically draw lines to each one of the dots, and then we cut it in half, perpendicular bisectors right here, and we kind of join them together. And that gives us, if we do it in the real space, it gives us a unit cell. If we do it in phase space, it gives us the first Brillouin zone. Awesome. Thank you guys so much for watching. Planck's constant is a little bit like pi in the sense that it's a constant. But the thing about Planck's constant is that it's it kind of has a similar thing to do quantization. Like, you could take to quantize stuff, you could say like n times h. So you're counting the number of h's that you have. And so this can quantize stuff. Like energy, for example. You could do HW, and then you can sort of quantize energy in a way. But pi can quantize, so this quantizes energy. This can quantize phases. So like angles, right? So this is h bar w. This is energy, and then this is kind of like how many phase shifts do we have. But they're a little bit different units. H is in terms of joules. So H is actually joules times seconds, and then this pi is an angle. So since the units are different, they can kind of do different things, but they both kind of quantize a little bit. in their own ways. So it's very good questions from you guys. And hell yeah, hopefully this exam is going to be too hard. Anyway, you guys have an awesome night. Thank you so much for showing up. That was really cool that we had some people through this stream. I'm going to give a little shout out to Swiruli, Dummers, and Ilavibin. Thank you all for showing up. Super awesome. Oh yeah, studying is really hard. I like to use flashcards and multiple choice quizzes to study, as well as like repeating my homework over and over again. Like I don't just do the homework one time, I do it a bunch of times. Similarly to like playing songs. Like if you play a song on guitar, you kind of want to play the song a bunch of times once you learn it. So that's why I try to do the same problem a bunch of times so I get like good at it. So you know, I know it's a little bit boring. I love you, Ben. All right, later, guys. Thank you so much.